Alright, so what we're going to do in this section is a different type of way of central tendencies. So what I want you guys to just do is look at these two data sets. So you have the first data set here. I know it's a little faded, but you guys have your books, right? Mean is 60 and median is 60. So you have this first data set of exam scores. And then on the bottom you have a second exam score portion. So what I just want to quickly do, you guys to do is, you see any differences and some similarities on both of them. Just, you can say it out loud, just think of them when it comes to it. Right there. Okay. Now, one thing I was hoping you guys saw, right? Notice sample sizes are actually pretty different, right? 13 and 11. That's one major difference. Hopefully, looking at the dot plot, you can see a couple differences as well, right? So one goes from 40 to 60. The other one goes from roughly 10 to 100. And hopefully, you notice the similarities is they have the exact same mean median, right? When it comes to both 60 and 60. So my question for you guys is, well, what if I did not give you the data set and I did not give you the graph? I just gave you this summary right here. That summary for the first one and this summary for the second one. Okay. Would you guys believe that they're the same data set based off that information? Probably yes, right? Just based off this. But we can tell there's some differences between one and the other, right? So that's what we're going to be doing in this section is figure, okay, how do we do this mathematically without seeing some differences when it comes to it? Okay. Now, unfortunately, this is the type of section we do in class and give you a little activity about. But since we're not in class, I'm just going to give you straight out the definitions, and we'll just go from there. So you should have a blank piece of paper on your portions of itself. And the first part we're going to talk about is something called the range. Okay. So the range is a little light. Get the purple one. So the range is the difference between the max value and the minimum value. Okay. So essentially, when it comes to the equation, the range is equal to max minus minimum value. Okay. And that tells us, how far the data values are from the closest, smallest to biggest. So it tells us if it's, narrow or very wide when it comes to it. So that's the first major difference we talk about when it comes to differences between each data set, especially when they have the same mean and median. Okay. So from that concept, we want to grow and expand from there. Is, well, what happens after that? So we have nice thing, but we want some more concrete examples when it comes to it. Okay. Now the next one we're talking about, again, we're going to do this a whole class activity when it comes to it, but obviously we're not in class. So I'm just going to give you guys the definition, and we'll just go from there. Okay. So the next concept is called the variance. And we don't talk too much in this class about the variance. It's more like if you go to higher stats itself, but it's just a quick, good definition anyway. So the variance is the average of the squared distances from the mean. Okay, and this actually has an equation. So the equation for the variance looks like this. So hopefully, guys, we're studying your notation purposes, right? X bar is mean, X is data values, and N is sample size. So using OR operations, we first subtract, then square them, then we add them, and then finally divide by N. So that's called the variance, okay? But the one we care about the most is actually the next one. Is called the standard deviation. This is the one we're going to be using a lot more itself. Okay? So the standard deviation, by definition, is how much spread out the data values are from the mean. Okay? So in other words, on average, how far a data value is from the mean. So now what this means is we can find individual data values to the mean itself. So how spread out, and then from there we can see, okay, given a smaller or larger standard deviation, that tells us a lot about the data set. Okay, so here's a little hint when it comes to standard deviation is the larger the standard deviation is, the more spread out the data values are when it comes to it. The smaller the standard deviation, the closer the data set is to each other. So just looking back at our class examples, right? So exam scores 1 and 2. Now we can find the standard deviation. We'll do it now, but now you can rank them just by looking at the data set, and the summary is which one will have a larger standard deviation than the other. So since this is farther apart, more spread out compared to this one, from 40 to 80, this will be a smaller standard deviation compared to the larger one. And that's one major difference we want to care about when it comes to it. So that's called a standard deviation. Okay. Now when it comes to standard deviation, we have an equation for that. Now, here's the problem. So remember I introduced population sample last time, so this is where it gets far more in detail as well. Okay. So here are 4 more notation purposes you're going to have to start slowly understanding as well. Okay. So when it comes to population standard deviation, the symbol that represents this is sigma, like that. So a fancy R. Okay. So you can think, fancy R when it comes to it. Okay. So this equation is very similar to the one on top. In fact, it's actually the exact same as the variance, except you take the square root of the variance to get this. So if you do this manually, you will get the variance before you even get the standard deviation itself. Okay. The sample standard deviation looks like this. It is denoted as little s, which is not too bad, right? Sample for s, and is the exact same equation except one very important difference. You divide by n minus 1 instead, which makes a subtle difference itself. Okay. Now, in most cases, we're always going to be using sample no matter what. Okay. Now, the good news is, since calculation can be done to this, most of the time it's going to be done non-manually. I will never ask you to find the standard deviation because it gets a pretty tedious framework when it comes to it. But it's good to know the equation itself and how to slowly break it down. Okay, when it comes to it. Okay. So what we care about the most is, okay, let's suppose we have a standard deviation. How do we use it, right? That's the the main thing when it comes to it. Things like that. So from that, it goes on to the next section. Part of this section is the very bottom is the Empirical and Chebyshev theorem. Okay, that's on the next page. Now, before we get there, again, like I said, right, we're going to do these types of graphs throughout the semester, but I give you guys a little bit more detail of each one. So again, I just quickly summarized the 3 major graphs. So hint, right, they're going to be very important going on, and we're actually talking about this in a little bit as well, because this is our perfect graph. So just a quick information on to summarize it. So normal distribution or bell-shaped curve is symmetric at both ends, meaning, right, it's literally cut in half. And we'll talk about what's the actual half marker itself in a little bit. Skewed right starts high, goes to the left. Skewed left goes the opposite direction. Okay. So just, fun little fact here. I just say, okay, using these templates, right, so using these 3 graphs, now you want to classify these histograms. So again, they're not going to be perfect, but you can see roughly what shape would they look like. So why don't you guys try them? So this is called, let's say this is A and this is B. What shape would they go, what do they look like? So you quick pause and just go and do it. All right, so if you guys tried it, so hopefully, right, this looks more like a skewed right graph. So skewed right graph because it goes up. The best way, you can just follow your pencil and you can see the framework when it comes to it. So same thing here. If you're not sure, you could just, okay, goes like this. And then it's, okay, roughly what that look like. And that looks like a skewed left graph, right, when it comes to it. So that's pretty much it. So once you make your histogram, you could tell the shape of it, just go by that kind of stuff. So like I said earlier, right, we're going to talk a bit more about the normal distribution. And why it's so perfect and so nice itself. Okay, so that corresponds to one of our very important rules called the empirical rule, right here. Okay, so the empirical rule states there's three criteria. So for a data set having a distribution that's approximately normal, that's the key thing. So this rule only works if it's a bell-shaped curve. In other words, a normal distribution. Okay, the following is automatically true. Okay, so about 60% of all the data values fall within one standard deviation of the mean. 2, about 95% of all the data values fall within 2 standard deviations of the mean. And then 3, about 99.7% of all the values that lie within 3 standard deviations of the mean.